This is a series of videos to look at the questions on Unit 4 of the AQA Chemistry paper from June 2014, which deals with Kinetics, Equilibria and Organic Chemistry. This video looks at question 1, which is an equilibrium question. The first question is fairly typical of the question set in that you are given some initial numbers of moles of substances in an equilibrium reaction, and you're asked to work out the number of moles at equilibrium given the number of moles of one of them, in this case G. So you're told that you have 0.8 moles of G, and at the start you have 2 moles and 1 mole of E and F. So make sure that you really clearly understand that at the start that there are 2 moles of E, so we put 2.0, and of F we have 1.0, and of course we have no G at the start. Once we reach equilibrium, we know we have 0.80 moles of G. Now, because the ratio in which they react is 1 to 2 to produce 2, we could say that the 2 moles produced was 0.8, which means that 1 mole would be 0.4. So 2 moles is the equivalent of 0.8, 1 mole would be the equivalent of 0.4. So, given that 2 moles of F has reacted, we know that 0.8 moles have reacted, and therefore this has gone down to 1 minus 0.8, which is 0.2 or 0.20. So the numbers of moles of F would be 0.2. The numbers of moles of E, well, this one, only 1 mole reacts, and that is the equivalent of 0.4, because 2 moles is 0.8, and so this will diminish down to 1.6. It doesn't really matter about the number of zeros that you put here, but clearly this one is given to 2 decimal places, and if you put a 0 there or a 0 there, that would not count against you. When you come on to Kc, Kc is a simple expression that can be learnt. It is the concentration of the products at equilibrium raised to the power in the equation divided by the reactants, the product of the reactant concentrations raised to their powers. So in this case, Kc would be equal to the concentration at equilibrium of G. So you're perfectly at liberty here to write EQM or indicate that this is at equilibrium. It's not necessary, however, and that would be squared divided by the concentration of E and the concentration of F raised to the power of 2. Those are multiplied together. Now, the concentration of all of these are measured in moles, so all concentrations are measured in moles per cubic decimeter. And so the moles per cubic decimeter here will cancel with these. They're both squared. So these will cancel with those, leaving 1 lot of moles per litre on the bottom. So the units will be 1 over moles to dm to the minus 3, which when you do 1 over will be moles to the minus 1 dm. You change the sign of both, dm to the 3. When you're trying to work out a Kc value given the numbers of moles, you must remember that this has to be concentration. So you must divide each part by the total volume. So here Kc will be equal to the concentration of G, which will be 0.85 divided by the total volume, which is 1.5, and that is squared, if we remember from the last part, divided by the value for E, 2.5, divided by the total volume, 1.5, and that's not raised to, well, it's raised to the power of 1, but is understood. And then we also have for the value for F is 1.2 divided by 1.5, and that is raised to the power of 2. So there's a number of things that you could do here. You could, if you wished, you could cancel these 1.5 squared with that 1.5 squared there. Probably no great reason to do that, and that 1.5 could go onto the top there. 1.5 could go to the top there, but probably it's much just simpler just to do the calculation, and it works out at 0.301, and acceptable answers included from anywhere from 0.299 all the way through to 0.304 would have been acceptable for that. So the marks really come from that final answer and from there. Now, when you come to change the volume, in changing the volume with a bigger volume, and you're dealing with an equilibrium which is in the gas phase, so just to double check on that, you go back to this question, you see that it's in the gas phase. If you increase the size of the container, you have got a lower concentration effectively of the gas. In other words, the pressure of the gas would diminish. So we're working under what could be described as now lower pressure. So if you have lower pressure, that means that any equilibrium reaction will move in the direction of fewer gas moles when you raise the pressure. But here we're not raising the pressure, but we are lowering the pressure because we have that. So the explanation will be that the equilibrium will shift in the direction of of more gas moles. Okay, because we have lowered the pressure. So in the explanation, we have lower pressure, which is not part of the answer. But if you understand that we have lower pressure, so the equilibrium will move or shift in the direction of more gas moles, which opposes the change. So, because we know there are more gas moles, if we go back to the original equation and toss up the number of moles, you can see that there are 3 moles of 3 moles of gas on the left, 2 moles on the right. So the direction of more gas moles is in the direction left of the product. So it is very important that you indicate the direction of more gas moles is the left hand side, or the reactant side, the left hand side. So the equilibrium shifts in the direction of more gas moles, which is the side away from G. So it's important to get the 2 marks that you explain that there are more gas moles on the left hand side and that the equilibrium shifts or moves in the direction of more gas moles. But this is, you must also explain very clearly that this is to oppose the change that has been made. So that's to oppose the reduction in pressure. Because more gas moles, if you like, will provide more pressure. So what has that done to the amount of G? Well, of course, you've moved away from G, so that will decrease G. Okay, and finally, on 1E, we have the mixture is allowed to reach equilibrium T2 in the same size same size as the original question, 1.5 dm cubed, but we've changed the temperature. The value of Kc was found to have increased. Kc has increased. That means the movement in the direction of the products, G, must be, if that has increased, then we can work out from the original information, which is that going from left to right is exothermic. When we've made this change, we found that Kc, the equilibrium, was increased. So there has been a move in the exothermic direction. which of course must come into the explanation. So the reason, state and explain which of T1 or T2 is higher. Well, when we go to T2, it moves in the exothermic direction, which means that T1 is the higher temperature. So why? Because as we move towards T2, if T2 is the lower temperature will encourage the direction to, or the equilibrium to shift in the exothermic direction to oppose the lower temperature. There's a movement in the exothermic direction. So how do we word this? How do we word that? We obviously, it's very important that you get T1, but how do you word that to make sure that you score the marks? You have to make it really clear that the forward direction is exothermic, and that simple understanding that that is exothermic will get you 1 mark. And then some statement that the equilibrium again, the equilibrium will shift to oppose the reduction in temperature or alternatively you could explain it the other way around. So the forward direction is exothermic and the equilibrium has shifted to oppose the reduction in temperature of T2, or you could talk about it in terms of T1. And that is how you score the 12 marks on question 1. This video looks at question 2 from the AQA Chemistry A-level paper, Unit 4 from June 2014, covering Kinetics, Equilibria and Organic Chemistry. This question looks mainly at acids and pH. A weak acid is a fairly standard definition that you need to know, which is that the acid would be partially dissociated. Or ionized. The reaction of propanoic acid with sodium carbonate. Propanoic acid is CH3CH2 COOH, C double bond OOH, and any acid reacts with the carbonate to form salt plus water plus carbon dioxide. So in this case we will get CH3 CH2 COO minus Na plus, which can be written in that form. There's no reason for state signs, it's only worth 1 mark. And so the other two products would be water and carbon dioxide. Because we have 2 sodiums here, we would need 2 of the sodium propanoates, which means that we would need 2 of the propanoic acid in that position. Now it is also possible that you could write this without the sodium ion because it's just a spectator ion, Na+, Na+. That would probably be acceptable and would be acceptable, and it's also possible that this carbonate ion might only be protonated once, in which case you could get the hydrogen carbonate that would be formed. So you would get 1 mole of this and 1 mole of sodium hydrogen carbonate. That's an alternative possibility. When you're asked for the pH of an alkaline solution for a hydroxide, you need to establish straight away that the calcium hydroxide its formula is actually important here, because calcium from group 2 hydroxide, the OH minus aqueous ion, means that when we're working out the concentration of the hydroxide ion, before we move on to work out the concentration of the hydrogen ion, we can see that if this is the concentration of the calcium hydroxide, then clearly each calcium hydroxide has 2 hydroxide ions, which means that the concentration of the hydroxide ion, which can be written like this, will be equal to 0.0240 which is, of course, twice the concentration of the calcium hydroxide, because each 1 mole of calcium hydroxide will produce 2 moles of the hydroxide ion. So this is an important step and will be worth 1 mark. You then, of course, do not need to work out the concentration of the hydroxide ion. You need the concentration of the hydrogen ion in order to work out pH. But you know that Kw here is 1 times 10 to the minus 14. So if 1.00 times 10 to the minus 14 is equal to the concentration of the hydrogen ion multiplied by the hydroxide ion concentration at this equilibrium, then clearly if we want the concentration of the hydrogen ion, which is what we're after in order to work out pH, it will be equal to your 10 to the minus 14, your 1.00 times 10 to the minus 14 divided by the hydroxide ion concentration, which of course we know to be 0.0240. And that would give you don't necessarily need the answer at this stage. That would be equal to 4.166 times 10 to the minus 13, which if you have been taught, you could convert that into POH and subtract it from 14. Sorry, not the 4.16, sorry, the hydrogen ion would be 4.16, but you could work out the POH, sorry, from working out minus the log of that. And so from this value of the hydrogen ion concentration, we can do that pH is equal to minus the log of the hydrogen ion concentration, and the hydrogen ion concentration is, of course, what we have just calculated, which is that. And so the answer comes out. You must always list your answer to 2 decimal places, and it comes out as 12.38. So the marks will come for the final answer, but also for working out either the hydrogen ion concentration or working out a value for POH. If you need to write an expression for the acid dissociation constant for the benzene carboxylic acid, then clearly all you need to do is, as we did with Kc in an earlier question, we just need the concentration of the products divided by the concentration of the products multiplied raised to the power in the equation, but on this occasion we have just 1 proton to be lost. So it's the concentration of the hydrogen ion at equilibrium, H plus aqueous at equilibrium, multiplied by the concentration of the anion that is then produced, the benzoate or the benzene carboxylate, as it should be called, C6H5COO minus, divided by the undissociated C6H5COOH. All of these are at equilibrium, but you're not required to do that, nor are you required to put in the units. You then have to work out the pH of a solution which has a concentration of 0.120 moles per litre and give your answer to 2 decimal places as usual. So what we do here is we assume that the benzoic acid's dissociation is small, and that when it dissociates it will produce 1 mole of H plus and 1 mole of the benzene carboxylate ion, which means that these 2 concentrations are the same. So the immediate thing that we can do is that we can say that the Ka is equal to the concentration of the H plus ion squared, because this is the same as that, divided by the concentration of the undissociated C6H5COOH, which we are going to assume is the same value as the original in calculations. So if we then rearrange, we can get to the point, so this would be certainly worth a mark if we were working towards it. We would then have that the H plus ion would be equal to bring this across, so Ka we've got a value of 6.3, so there's the Ka up there, 6.3, 1 times 10 to the minus 5. We would then multiply that by the concentration, which we have got as 0.0120, and because the H plus is squared, we would then square root that value there. Okay, and that would, again, it's not necessary to write out the answer to that. 8.70 times 10 to the minus 4 moles per litre, but pH would be equal to minus the log of this number, which of course is this number here, and that works out as 3.06. Two D is a buffer calculation, which some people sometimes regard as some of the hardest calculations to do. We are asked to make up a buffer solution with a pH of 4 is used by using the benzene carboxylic acid and sodium benzene carboxylate. Calculate the mass of sodium benzocarboxylate, MR of 144, that should be dissolved in 1 litre of a 0.01 molar solution of benzene carboxylic acid to produce a buffer with a solution of pH 4. The first thing that you might want to do then is to, of course, establish that if you've got a pH of 4, then you're aiming for a hydrogen ion concentration of 10 to the minus 4. So we have rearranged the idea that pH is equal to minus the log of the hydrogen ion concentration. We have rearranged that so that we have made the hydrogen ion, the concentration of that, the concentration of the hydrogen ion will be equal to 10. Use the minus across to the other side to the 10 to the minus pH. So here we've got 10 to the minus 4.0, which of course is equal to 1.00 times 10 to the minus 4 moles per litre. That is the concentration. And doing that little piece of work would certainly get you 1 mark. You then have to appreciate that if we use our dissociation constant from the last question, so if we go back to this relationship here and rearrange, we can make H plus the subject of this particular relationship. So if we rearrange this equation, we can say that H plus is equal to Ka multiplied by the concentration of the benzene carboxylic acid divided by the concentration of the benzene carboxylate. So we then get to a position where we know that our value for H plus would be equal to Ka, our H plus itself will be equal to Ka multiplied by the concentration of the benzoic acid divided by the benzoate. However, they're asking you for what mass of sodium benzocarboxylate do you need, benzene carboxylate do you need? So we need to find the concentration of the C6H5COO minus. So let's remind ourselves very quickly of what Ka is equal to. It's equal to H plus multiplied by the C6H5COO minus divided by C6H5COOH. So if we rearrange that, we know that the concentration of the salt would be equal to Ka multiplied by, so we bring that up to the top, by the concentration of the undissociated, of the acid divided by, of course, the value of H plus. Okay, so we know quite a bit of this already. We know that we've got 1 litre in total. We've got a concentration of the benzene carboxylic acid. We know then that Ka is going to be equal to 6.31 times 10 to the minus 5. It's not really clear, but this in fact would be exactly the same concentration as you have there. So that would be 0.0120. The reason why it hasn't changed is because its dissociation has been prevented to a degree by the presence of this benzene carboxylate in the equilibrium. So we can just take it at that, and then that is divided by your 1.00 times 10 to the minus 4. That gives an answer. So we have already established probably that through this little bit of calculation we certainly get a mark there. The correct input of the values would certainly get a mark there. Perhaps an indication of the value at this point would get a mark, which is 10 to the minus 3 moles per litre. And so that's the number of moles, but we're in 1 litre, so it is also the number of moles of this particular thing that we need. And so to work out the mass is equal to moles, so the mass will be equal to, of course, moles times mR. And so the answer will be, mass is equal to moles times mR. May have missed out a bit on that. And so that is equal to the value there multiplied by the 144 value that we have up there, and that leads to a value, so times your 144.0, and that is equal to 1.09 grams. Okay, so some important things about buffer solutions as we move through this is that when you have a buffer solution, the dissociation of this is hindered by the presence of this, and the ability of this to take on a proton is hindered by the presence of that, so that we're able to use this concentration 0.0120 to represent that concentration, because dissociation has been prevented by the presence of this. And finally, two solutions, one with a pH of 4 and the other one with a pH of 9, were left open to the air. The pH of the pH 9 solution changed more than the other solution. So the alkaline solution changed more than the acidic one. Suggest what substance might be present in the air to cause the pH to change. Well, of course, the obvious thing is the substance in the air is, of course, carbon dioxide is an acidic gas. You possibly would be allowed other acidic gases like oxides of nitrogen or sulfur dioxide. And then, of course, what would happen is that if you've got carbon dioxide, that will neutralize the alkaline solution, and so will lower the pH. So that this will get you the 1 mark. The explanation is that the CO2 is acidic and neutralizes, and so the pH of 9 will decrease, and decrease I guess reasonably rapidly. The third mark, of course, is that we have got the idea that carbon dioxide is acidic. So those 3 marks are relatively easy to obtain. Question 2. This is a video to look at question 3 from the AQA A-level chemistry paper, Unit 4 of June 2014, which looks at kinetics, equilibria and organic chemistry. This is a kinetics question. You are given a table where you are given 3 experiments. You're given concentrations of 2 substances, A and B, and an initial rate of reaction in moles per litre per second, moles per cubic decimeter per second. The reactions, you're given no information at all about orders, and so it's not possible to work out a value of K at this particular point. So in some questions it's always worth looking forward to see if there is a way of working out what K is before attempting these table type questions. However, on this occasion we have no choice but to try and work it out on inspection. So what we do is we look for a situation where the concentration of something does not change. So here you can see between experiment 2 and experiment 3, B has not changed its concentration. So what we can do is just look at the effect of changing the concentration of A from 2.4 times 10 to the minus 2 to 3.6 times 10 to the minus 2. So we can see immediately that this is an increase of what, 36 over 24, 3.6 over 24, which is an increase of 1.5, an increase of 1.5, an increase of 1.5. I will express that as an increase of 3 over 2. We then look at how the rate of reaction has increased. One way of doing this is to go 4.05 divided by 1.80, or more simply perhaps 405 divided by 180. When you do that calculation, that value comes out at 2.25. But of course 2.25 is, as a fraction, 9/4. And you can see therefore that as you've increased the concentration of A by a factor of 3/2, the rate of reaction, when B has remained the same, has increased by 9/4. And you can immediately see the relationship between these two numbers. You can just think of this as increasing by 1.5, and this hasn't increased by 1.5, but has increased by 2.25. And of course 1.5 squared is 2.25. 3/2 squared is 9/4. So an increase of 1.5 has caused a 1.5 squared increase in the rate of reaction. So we can work out immediately that the order with respect to A is second order. If we then go back into the table to work out what B would be, we need to see B changing. So if we look at this situation then between, let's say, here and here, we can see that A has again increased by 240 over 160, or 2.40 over 1.60, 24/16. It is exactly the same increase, 3/2. So if this were zero order, this would increase by yet again a factor of 2.25. So if we take the value of 8.00 times 10 to the minus 5 and look at how many times that has increased to make 1.80 times 10 to the minus 4, if it again comes out as 2.25, we can see that this has made no difference to the increase. And if we do 18/8, it does indeed come out at 2.25, which means that the change in concentration here has made no difference whatsoever to the effect of A. So we can see from this that the order with respect to B must therefore be zero order. We're then given a different situation with C and D. We're given the rate equation and we're asked to calculate the value of the rate constant. So this is just another rearrangement. So we would know that K would be equal to, rearrange it, would be the rate, in this case the initial rate, and divided by the concentration of C and the concentration of D squared. And the units are needed as well. So all we would do is we take the initial concentration of C as 4.55 times 10 to the minus 2 and plug it into there. We would take the value of D of 1.70 times 10 to the minus 2 and plug it into there and square it, multiply them together, and the initial rate of course is here. And we would put that into there to obtain an answer. So we would be getting 1 mark for that being 6.64 times 10 to the minus 5 divided by 4.55 times 10 to the minus 2, but also divided by 1.70 times 10 to the minus 2 squared, and that answer comes out at a value of 5.05. And the board allow answers in the range of 5.03 to 5.07. So a mark there, and of course the rate constant units can be worked out by plugging them into this relationship. So you have moles per cubic decimeter per second, which is always the units of the rate of reaction, divided by moles per cubic decimeter for C, and that you can see straight away cancels with the one above. And then we've also got moles to the cubic decimeter squared, So that would be moles squared dm to the minus 6. This would cancel with that, leaving you with seconds to the minus 1 over moles to the squared dm to the minus 6. When it is over that number, you just simply change the sign on the bottom. So this will now read moles to the minus 2 dm to the 6 seconds to the minus 1. And finally, we're doing a new experiment, but this time the total volume of the mixture is doubled, which means that all concentrations are halved because you've got twice the volume, which means you've got the same number of moles in twice the volume, which means that all concentrations are halved. Which means if we go back up to here, we know that that is halved and that is halved. Can you see that if you've got this halved and this one is halved but squared, that would be a quarter. So we would have a half multiplied by a half squared, which is a quarter. So it would be so that would equal a change of 1/8. In other words, you have changed your concentrations by diminishing them by 1/8 in this expression. So all you need to do is to take this value of the initial rate. The initial rate would be 1/8 of this initial rate. So it would be 6.64 times 10 to the minus 5, and it's 1/8 smaller than that. So you divide that by 8, and that will come out at, 8 into 64 go 8 times 8, 24, 3 times, so 8.3 times 10 to the minus 6 will be the rate of reaction. No units required in this because it's only worth 1 mark, but it would be moles per cubic decimeter per second. Sorry, just to run through that again. The initial rate is reduced, as we said at the top, by 1/8, and so when we come back down here, we take the initial rate and it will be reduced by 1/8. 8's into your 664 go 8.3 times 10 to the minus 6. Units not required because it's only a 1 mark question. This is question 4 from the AQA A-level chemistry unit 4 of June 2014, dealing with kinetics, equilibria and organic chemistry. Question 4 is an organic chemistry question. Name the strongest type of interaction between polymer chains of Kevlar. Spotting that within the chain, this long chain, there is a delta minus oxygen and a hydrogen with a delta plus will lead you straight away to the idea that there would be hydrogen bonding. Suggest why the reaction of ammonia with X in stage 1 might be considered unexpected. Well, ammonia, of course, is normally associated with nucleophilic substitution, nucleophilic addition elimination, or possibly as a base because the nitrogen has a lone pair. And so a statement that, of course, that ammonia has a lone pair would probably get you a mark. So there is a lone pair, but that lone pair, of course, means that it is very likely to be not an electrophile, but a nucleophile. It would be an electron pair donor, not as looks in this particular case as if it's going to attack into a benzene ring. So, of course, benzene itself benzene would usually repel something with a lone pair of electrons. So something along the lines that benzene will repel a lone pair, or benzene will repels lone pairs or nucleophiles would get you the second mark. You could probably also talk about it in terms of benzene would undergo electrophilic reaction, electrophilic substitution, rather than a reaction with a nucleophile. Suggest a combination for the reactions in stage 2. So stage 2 turns an NO2 into an NH2. NO2, nitro group, into an amine group, is done traditionally with a combination of tin, SN, tin, with usually concentrated hydrochloric acid. But certainly, as it's only a one marker, tin and HCl would work. But other combinations would work quite nicely. The common material that adds across a double bond, so you could also have hydrogen with a nickel catalyst, perhaps hydrogen with a platinum catalyst, even other combinations perhaps of hydrogen gas being produced by a combination of perhaps iron and concentrated hydrochloric acid. Compound X can be produced by the nitration of chlorobenzene. Give a combination of reagents for this nitration of chlorobenzene. If you're going to nitrate, the reagents that are always expected for this are any nitration of a benzene ring. You need to make sure that you include the words concentrated, conc is allowed, with nitric acid, and then be very careful not to write then and sulfuric acid, because then it's not clear. You must also write that the other reagent would be concentrated sulfuric acid. Okay, no reason for you to put the AQ sign in or indeed to expand upon that. The equation is that these two combine. You can either learn it as one equation, which is probably more straightforward, or you can remember that the sulfuric acid is a stronger acid and protonates the nitric acid, which then decomposes into the NO2 plus ion, which is the thing which is going to, the species which is going to attack the benzene ring. So how do we write it as one? Well, what we would need to do is we would need to have your nitric acid being attacked by the sulfuric acid, and the formation of the nitronium ion, which is going to attack into the benzene ring, would mean that we'd need 2 moles of the sulfuric acid, 1 mole to first of all protonate the nitric acid, but the second mole of sulfuric acid for removing the water from the protonated nitric acid. So you would then be left with H3O plus and 2 moles of HSO4 1 minus. So, as I say, you could write it as 2 equations. One equation where 1 mole of this reacts with that to form NO2 plus HSO4 minus, and then the H2NO3 plus from the protonation of this then reacts with another mole of this to produce 1 mole of that and the nitronium ion. Sorry, 1 mole of the nitronium ion, or by just decomposition. So if we're looking for the formation of X from chlorobenzene, what we've got to do is to take the chlorobenzene, and we have got to nitrate it in such a way that we are able to form the product. So if we just look back very briefly at the if we look back here, we can see that the nitro group that's going to attack is going to attack in the 4 position. And so when we do the mechanism, we must stick with that. So the name of the mechanism is electrophilic substitution. And the mechanism will occur if we need to draw the chlorine away from where we're going to attack in with the nitro group. So if I start with our benzene ring with the chloro group, let's put the chloro group in this position here so that I attack into this particular area. I need to bring my NO2 plus into this area. You can draw it with 2 double bonds. It's probably just easier to put NO2 and then put the positive charge clearly on the nitrogen. The first mark is almost certainly for the position of the chlorine in the correct position. The electrons are then going to move, a pair of electrons will move from the ring to form a bond between the carbon, which is at 2 o'clock, and the nitrogen. That will produce an intermediate, so that we will have the Cl again attached, and then we have the benzene ring. The ring has been broken open, and there would be no electron density in this region. So you start a horseshoe shape to occupy that area, and it will have a positive charge. There will be one bond to the NO2, and you now at this point show the bond to the hydrogen, which hasn't been shown up until this point. The electrons then return. You don't have to show what happens to the H+, but you need to show that the bond pair of electrons reverts back to the ring. So the marks come from one for the electrophilic substitution. Effectively, you have got a mark for the NO2 attacking into the right position, so there's effectively one mark there. There's one mark for the intermediate correctly shown, and then one mark for it returning with the correct curly arrow. This video looks at the AQA A-level chemistry paper from June 2014, Unit 4, Kinetics, Equilibria and Organic Chemistry. Question 5. This deals with organic chemistry. The carbonyl compound, propanal, reacts with HCN. The mechanism would be nucleophilic addition. Outlining a mechanism would involve drawing curly arrows. It is important that the double bond oxygen is correctly connected, C double bond oxygen is correctly connected to the hydrogen and to CH3CH2, which of course could be abbreviated to C2H5, write it as CH3CH2. The cyanide ion from the hydrogen cyanide is the attacking nucleophile. It's important that you could put a triple bond in here for the carbon triple bond nitrogen, but it's essential that you understand that there is a lone pair on the carbon, and that carries a negative charge. The curly arrow goes from the middle of the lone pair to form a bond between the carbon and the carbon, and simultaneously the double bond breaks open and the bond pair becomes a lone pair on the oxygen. So there are already marks that will be allocated for each of those steps. So the attack by the cyanide ion and the movement of the electrons to the oxygen has already got a mark apiece for those. The structure of the intermediate then will be CH3, CH2, C. O will then have a lone pair and a negative charge, and there will be a hydrogen and a cyanide group on there. The final part of the mechanism would involve a H+ from the hydrogen cyanide and a curly arrow from that lone pair to a bond pair to create a bond between the O and the H. The marks of course will come for the correct structure of the intermediate and that final curly arrow for those 4 marks. The final step of course is just simply to write out the product, which would be good practice, but the marks in fact are allocated prior to that formation. So this goes to there, and that would then go to the product. If we look at the product, so if we look at the actual structure of the product will be a C attached to an OH, attached to a CN, attached to an H, and attached to C2H5, CH3CH2. Now that is a carbon which is attached to 4 different groups, so it is optically active, which means it produces enantiomers, and there will be a 50% combination of the 2 enantiomers. So let's draw the structure of each enantiomer, which are non-superimposable mirror images, to show how they're related to each other. So you would certainly need to show 3 dimensions. This representation is not good enough, so you would need to draw one it doesn't matter how you draw it as long as you have show some sort of three-dimensional nature. So one good way of doing this might be to use a triangle that comes out towards you to show perspective, and that might be attached to, let's say, the hydrogen, and then one going back into the paper which will be attached to the CN. But it doesn't matter what combination that you do for each of those pictures. To show the idea of the enantiomer, you then need to have a mirror and then draw in the structure. It doesn't matter whether you put the OH a different way around. Of course, that's irrelevant because that bond is fully rotating. So if we then bring the carbon in here, we would have a wedge coming out with the hydrogen on it, a wedge going back with the CN on it, and then in the plane of the paper, we'd have a CH2, CH3. Now, this is not the only acceptable answer. If this is shown without the wedges, but it is clear that you've got perspective there, that is permissible. But plus also, you can present this information in any order here. So this could be CN, this could be OH, or any combination. You just have to have the 4 different groups around the carbon for those 2 marks. So what 1 mark is, if effectively it says draw the structure of each enantiomer to show how they're related to each other, and so that is how you get the 2 marks for that. State and explain how you could distinguish between the 2 enantiomers. Because they're non-superimposable mirror images, the only way in which they differ is in their ability to rotate the plane of polarized light. So to score the marks, you need the idea that you have got plane polarized light. So the way in which you would do this is you would shine plane polarized light through the samples, and they would rotate each sample, each enantiomer, rotates, so this is the important part of the answer, rotates in opposite directions, and it may be important in other questions but not here to appreciate that that is in equal and opposite directions, so it rotates in opposite directions to score the marks there. The UPAC name for this product, so we have this product here, 1, 2, 3, 4 carbons, so it's a butane, and it's also a nitrile, so it's butane nitrile, and the hydroxy group is on carbon number 2. So this will be 2-hydroxy butane nitrile. Given that Ka is 4 times 10 to the minus 10, a relatively low number, in practice KCN rather than HCN is added to the carbonyl compound. Given that the Ka suggests why the reaction with HCN is very slow. Well, what that means, of course, is that the initial attack comes from Cn minus, and if this is a weak acid, so you would probably immediately get a mark for identifying that it would be a weak acid, and therefore the dissociation would be small, or by writing that the dissociation of HCN into H plus and Cn minus would be low. You have an appreciation, therefore, that the concentration of the cyanide ion, which is our initial nucleophile of the cyanide ion, is, of course, therefore very low. And if it is low, that means that the rate of reaction, the rate will be slow, because the initial nucleophilic attack will be dependent upon the cyanide ion attacking. That's where the 2 marks come from there. And it moves on to some ideas about general reactions of acrylic fibers. So there's the acrylonitrile, and it says write an equation for the reaction between propene C3H6, that's between propene, ammonia, and oxygen. And it's going to form the compound, which is of course as above, so that then will produce our CH2 double bond CH CN. So all that is required, of course, is some balancing for that. So if we run through the balancing of that, you'll see that the carbons are correct. The nitrogens, of course, are also correct. So if we are going to bring in some oxygen, the other product, the other likely product is going to be the other product. If you see, it won't involve nitrogen. We've already balanced there. We've already balanced the numbers of carbon. So it's a hydrogen-oxygen combination, which of course would be water. So given that we have got 6, 7, 8, 9 hydrogens there, we have 2, 3 hydrogens there, we need to have 6 hydrogens in total, so this will require a 3 in front, and that means that we now have 3 oxygens, so the number here would be 3 over 2. So obviously if we were to double this to 2, 2, 3, 2, 6, that would also be an acceptable answer, but that would be the correct answer for this. The term copolymer is used to describe the product obtained when 2 or more different monomers form a polymer. Draw the repeating unit of the acrylic copolymer that contains 75% of the acrylonitrile and 25% of a chloroethene monomer. So if you're going to do a repeat unit, you've got to have 3 times as much of this repeat unit compared to that. So all you need to do is to have fundamentally 3 lots of, so in your long chain, you have a series of carbons, and all you have to do, so this would not be a definitive answer, you would draw that number of carbons so that 3 of those units would come from the acrylonitrile, and 3 of them, and 1 of them only would come from the chloroethene. So there's loads and loads of ways of doing this, so there's no point covering all of those answers, as long as you have put in something. So if we put the nitrile first of all, so if we put the CNHH and repeat that, let's just repeat that one 3 times. So if we repeat that 3 times, and then finally we need 1 chloroethene. Well, that would, doesn't matter which way around we will do that, but it's likely that the chloro perhaps would be in that position, but it's not really necessary to go for that. But basically we must draw this, and it could be in any order as long as we have 3 times as many of those as that. I mean, it's the repeating unit, and you need to draw all of that as a repeating unit. And the type of polymerization, of course, involved will be breaking this double bond here. So it's the breaking of that double bond, and so that is, of course, addition polymerization. This video looks at the AQA Chemistry A level, Unit 4, Kinetics, Equilibria and Organic Chemistry from June 2014, and looks at question 6, which is about amino acids, organic chemistry. The UPAC name of lysine. Lysine has 1, 2 and 4, 6 carbons. It is a carboxylic acid, so it is hexanoic acid. And it has an amino group on carbon number 2 and also on the final carbon, carbon number 6. So it will be written 2, 6 dash diamino hexanoic acid. You're then asked to say how it would react with an excess of aqueous hydrochloric acid, which is a proton donor. There are 2 basic groups. The 2 amino groups are basic, and because we have an excess of hydrochloric acid, those 2 amino groups will be protonated. So it will be CH2 4 times. The protonated form of the NH2 will be NH3, and the nitrogen carries a positive charge. The carbon then will also have another nitrogen on it, which will be then NH3, and the nitrogen will again carry a positive charge, and then you still have your COOH and your H there. In an excess of aqueous ammonia, well, in the case of lysine, you have got just one acidic group, the carboxylic acid group, so this time the NH2 groups will be as usual. So that will then go CH2 4 times. This will still be NH3, but the final COOH will be deprotonated in the presence of alkali, the sodium hydroxide. The hydroxide ion will remove that proton or react with that proton, and that is the structure of the product in aqueous sodium hydroxide. With methanol, you have a carboxylic acid present, so acid plus alcohol goes to ester plus water in the presence of concentrated sulfuric acid. So on this occasion, what will happen is that the C double bond OOH will become a methyl group. So this could be drawn, you could draw this out fully as OCH3 to show the ester, or alternatively that can of course be written just simply COOCH3. Now in this particular case, of course, we're in a small amount of concentrated sulfuric acid, so there is of course a question mark about whether the amino groups that you've got on the chain in the situation where you have got concentrated acid, that would probably protonate. If there was sufficient of it, it would probably protonate the amino groups, but you would get a mark whether you protonated them or not. So if you just left it as NH, sorry, I've made a mistake on this one here, it's NH2 of course, NH2, there you would have CH2 4 times, and that would end in NH2, but if either of these or both of these were protonated, then that would be perfectly acceptable because you're in concentrated sulfuric acid. Mass spectrum of the alanine. So the alanine is there. The mass spectrum fragmentation is no longer on the AQA course. And so I'll run through this very quickly indeed. Write an equation for the fragmentation of the molecular ion of alanine to give an ion that produces this peak. So if we take the alanine CnH2 CH3, when it goes through the mass spectrometer, it will become a positive ion, but it actually not only becomes a positive ion, but it would also become a free radical as the electron has been removed, leaving an unpaired electron. So when it breaks up by fragmentation in the mass spectrometer, it's going to give a positive ion which has a value of 44. So you have to think of something which might add up to 44. So one thought might be CO2, but unfortunately the CO2 is attached to an H, so that would make 12 plus 16 plus 16 plus 1, which would be 45. So that doesn't look as if it is going to produce the correct value. If we look here, we've got a carbon, 2 carbons, 4 hydrogens, so that would give you 28. 28 and the 14 would give you 42, plus those 2 there gives you 44. So that it looks like the likely fragment that gives you the 44. So if we add that, we've got this one as a fragment, would have a positive charge and would give you your MZ peak at 44. And you would then have the positive charge would effectively be here, but that may not be necessary to indicate where you put the positive side. And then the other part that comes off, COOH, is not positively charged, it is a free radical. The free radical would actually be on the carbon, but you could probably put that into brackets and go from there. Okay, no great detail on that because it's no longer on the syllabus. Draw a dipeptide from 1 molecule of lysine and 1 molecule of alanine. So again, where we have these two, we could combine, a very simple thing to do would be to combine the carboxylic acid group there with the amino group there, for example. So all we would do to show a structure would be to draw out the lysine, NH2, CH2 4 times, C, NH2, H, and then we have the reaction between the carboxylic acid and the amino group, so it would go C double bond O NH, which we can write CO NH, which is a clear structure for that, and then you would go into the lysine, so that would then go C, and then that would be attached to COOH, and it would also be attached to a CH3, and of course if you have a look down a little bit lower, then from there you can see that if there's the CH3 attached, we've also got a hydrogen attached there. Now that is not the only answer. That is not the only answer. You could write this as C double bond O NH. That would be perfectly acceptable. Well, in fact, probably preferable in some ways. COONH, so you actually show it in full structure. You might also perhaps have done it the other way around, so using the COOH of the alanine with the NH2 group, either of these two NH2 groups. So there are several answers that would be acceptable for that, for a combination of lysine and alanine. So just why lysine leaves the chromatography column after the alanine. Well, it's being hydrolyzed in acid conditions, it says. So if we remember back to our answers for acid conditions for our lysine, you can see that under acid conditions it would have 2 plus charge, a 2 plus charge. Whereas the alanine, which has a structure with only one amino group, in acid conditions it would have a 1 plus charge. The column is packed with a resin which acts as a polar stationary phase. So it's a charged stationary phase, which means of course that the 2 plus charge on the lysine would mean that it would adhere to the stationary phase better than the 1 plus charge on the alanine. So in order to get the marks, you just simply need to make it clear that the lysine has a 2 plus charge, has a greater charge, and then the idea that that would adhere, stick to the stationary phase. There will be a greater attraction, so it adheres better to the stationary phase. This is a video that looks at the AQA A-level chemistry paper, Unit 4 from June 2014, Kinetics, Equilibria and Organic Chemistry, and looks at question 7, which is an organic question. Two esters have got a proton NMR spectrum. The two esters, it says, deduce which of the two esters produces the spectrum shown. In your answer, explain the position and splitting of the quartet at 4.1 in the spectrum. Predict the delta value of the quartet peak in the spectrum of the other ester. These esters are very similar. There is an ethyl group attached here to the oxygen directly, and here there's an ethyl group attached to the carbonyl carbon, the C double bond O. This will make a difference to the delta values of the protons in these environments here. So what we need to do is to look at the data sheet. The data sheet gives most of the answers here. On the data sheet, it is clear that if you have got a proton on a carbon, which is part of an ester that is attached to the oxygen through a single bond, you would get an absorption at 3.7 to 4.1. If, on the other hand, it was a carbon that is part of, if you like, the carboxylic acid part of the ester and is directly attached to the C double bond O, that proton will have an absorption at 2.1 to 2.6. So when we look at the question, we can see that this carbon here has protons on it, which would give you these somewhere around the 3.7 to 4.1 area, whereas these protons here would give us a value between 2.1 and 2.6. So when asked the question, which of the two produced this spectrum, you can see that there is something at the 4.1 area, and that is a quartet. If it's a quartet, that means that it is next door to a carbon which has got 3 protons on it. In other words, a quartet indicates 3 adjacent protons which are non-equivalent. So what we're looking at, of course, is an isolated CH2 group which is next door to a CH3. So where we have got the quartet, that tells us that is the CH2 which is next door to a CH3. So can we see from here that if this is the CH2 which is next door to the CH3, that would have an absorption at 3.7 to 4.1. So the first thing is that this is ester 1. This is ester 1. And we've got that from knowing that the quartet is at 4.1. So we can answer this question straight away. Predict the delta value of the quartet peak at the spectrum on the other ester. Well, clearly, if you've got the quartet for this one, will be a quartet, it'll be between 2.1 and 2.6. So the final answer, right down the bottom, would be 2.1 to 2.6 would be the delta value of ester 2. And that would get you a mark. Ester 1 would also get you a mark. But it also then says, in your answer, explain the position and splitting of the quartet at 4.1. So you would need to make it very clear that the quartet is created because you have got the CH3 group next door, and that the value of 4.1 is because from the data sheet that is a value that you would have. So the first thing is you get a mark for talking about the peak at 4.1, and that's as a result of a proton which is on a carbon which is next door to an oxygen of the ester grouping. So you'll be looking at that proton. So some sort of indication that you understood that 4.1 was the position for it. And the idea of it being a quartet and therefore adjacent to a CH3 group, which would indicate that you've got this being a CH2 group next to a CH3 group. And so that's where you would get the 4 marks from for that. So 1 mark for identifying ester 1, 1 mark for appreciating you worked that out because there is a quartet at 4.1. 4.1 would indicate that the proton you're looking at is in this position relative to the ester. This is from the data sheet. And then 1 mark for explaining that the quartet would be created because the CH2 group is next door to a CH3, and that would cause a quartet pattern. That's 1 mark for that. And then that you would be able to see that if it was the other way around and you had ester 2, then that same quartet, that quartet would be at 2.1 to 2.6. On to part B. This is a question then about, well, that structure is a quaternary ammonium salt. And so it says, name this type of compound. So you don't need to name it specifically here. You just need to name what type of compound. So it is a quaternary ammonium salt. It's actually a quaternary alkyl ammonium salt, but you'll certainly be fine with this as a compound. If you wrote quaternary ammonium ion, the mark scheme doesn't make it clear, but that's not the compound, so you wouldn't get a mark for that. Give the reagents that must be added to the original CH3 CH2 15 times NH2 to make the centromide. Well, you've got to add on an extra 3 lots of CH3. Now the way this occurs is by this would attack into a haloalkane which had 1 carbon And because we are given bromo in the structure, we are talking about the idea that you have got CH3Br, and the amino group will attack into this carbon, and there will be nucleophilic substitution, and the Br will go out, and the nitrogen from here would come into this carbon here. But that would have to happen 3 times. So it is also very important that you understand that you would need an excess of this bromomethane. So that's already getting you 3 of the marks. The reaction conditions would be the excess of that. Name and the type of reaction is, of course, nucleophilic substitution. Give a reagent that could be used in a test tube reaction to distinguish between benzene and cyclohexene. Slightly different topic. Describe what you would see when the reagent is added to each compound and the test tube is shaken. So the obvious reagent, of course, is that the cyclohexene has a double bond, whereas benzene's double bonds are delocalized. And so therefore we're looking, the principal one that would be fine would be bromine. Either bromine usually bromine would be in water, but it could be in a mutual solvent. But Br2 is the essential bit for getting that. It says, so it just says give a reagent, so you can write bromine, bromine water, bromine in a solvent. So bromine gets you 1 mark. With the benzene, of course, there would be no visible change. So they like AQA like this expression, no visible change. Whereas with the cyclohexene reaction, then you would get a color change from orange to colorless. So I think as long as you write does it decolorize, so as long as you're aware that it decolorizes, but obviously that would be orange to colorless. This video is about question 8 on the AQA A-level chemistry paper, Unit 4, Kinetics, Equilibria and Organic Chemistry, from June 2014. This is an organic question. Compound H is a cyclic ester formed by the reaction of a hydroxy acid or acyl chloride. It seems to be an internal attack. So what would be happening here is that the lone pair on the oxygen will be attacking into the C delta plus on the acyl chloride. So when it comes to name the mechanism will be nucleophilic addition elimination, which is always the mechanism for reactions on the AQA board for acid chlorides. Outlining your mechanism, of course, requires you to do curly arrows again, and so you might set it up in a way which enables you to see that internal attack more clearly. So if we place these in these positions, and then the attack from the oxygen could come from, let's say, there. So the lone pair of the oxygen is going to be responsible for this initial attack. So the attachments are, if we go back to the top, we've got 1, 2, 3, 4 carbons in between. So if we were to go CH2, 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 and then the OH, we have set up this perfectly for this particular reaction. So what happens, of course, is that this lone pair will attack into this C delta plus to form a bond between the oxygen and the carbon, while simultaneously this will push the bond pair of the double bond onto the oxygen as a lone pair. So far we have scored 1 for the name, 1 for the correct curly arrow from the oxygen lone pair to a bond pair with the carbon, and then from the bond pair to the lone pair with the oxygen. So we have already scored 3 marks. Then we might draw out the structure that is then made. Obviously, the oxygen has formed a bond, so we can run through this in any way, but we might put the structure with the oxygen in the same position, has formed a bond with the carbon, which has then got a lone pair and a negative charge on the oxygen. This is still attached at this point to a hydrogen and will carry a positive charge, and then all of the remainder attachments are the same, Cl, and then we've still got CH2, CH2, CH2 and CH2 before we get back to the oxygen. So at this point we can finish the mechanism by returning the C double bond O. The chlorine will leave as chloride and the proton will effectively be removed as H+. So the correct curly arrows for the remainder, which of course is 3 curly arrows. So the structure of this part is that the structure only scores 1, but these remaining 3 curly arrows, rather remarkably, only score 1 mark. The chlorine breaks off as the chloride ion, so a bond pair becomes a lone pair. There is the re-establishment of a double bond, so this lone pair becomes the bond pair as a double bond, and this bond pair becomes a lone pair to return the value to the oxygen. So those 3 curly arrows done correctly, rather remarkably, only 1 mark. The 2 remaining marks come from looking at table C on the data sheet to work out the delta values using carbon 13 NMR. So if you look at the 2 carbons labelled, you've got a carbon which is next door to a C double bond O for A, and you've got a carbon next door to a single bond to an oxygen, and then also attached to a C double bond O, although these are probably not specified. In a general sense, this is a carbon in a carbon-carbon bond, so it's probably going to be somewhere between 0 and 50. This is a carbon single bond oxygen, so it's probably going to be somewhere around about 50 to 100. But you have the data sheet, so you don't need to worry about those details. So if you look at the data sheet, you'll see that if you have got a carbon-carbon 13, and you look at table C, you can see straight away that if you have a carbon which is attached to an oxygen, which is then attached to a C double bond O and in the form of an ester, that one will be between 50 and 90. Whereas if you have got a carbon which is part of a bond to a carbon that is then a carbon-carbon single bond, but that carbon is attached to a C double bond O, that will appear between 20 and 50. So A, let's simply write this here. A is a carbon next door to a C double bond O, so this will be between 20 and 50, whereas this one is next door to an ester group through a single bond oxygen, so that will be somewhere between 50 and 90. And those are the 2 further marks to achieve the 7 marks in this question. To achieve the 7 marks in this question. 50 and 90 and through to that. The same molecule that formed the cyclic compound can also form a polyester. Well, in that case, of course, rather than react, this oxygen lone pair, rather than react with itself, can react with another molecule of this compound. So to draw the repeating unit, of course, what you will need to do is to make sure that you don't make any mistakes in terms of putting things down that are repeating further. So you want to start at a particular position. So you might start with this oxygen. So if we say that this oxygen has attacked in, so into another molecule, that oxygen then is attached to CH2, then to CH2, then to CH2, then to another CH2, and then this is where we would be attacking, so that it then goes C, double bond O, and it's the O which will attack into this position. So at this point we know that if we were to write another O, it would be the same as this O here. And so it would no longer be the repeating unit, then you would be duplicating this oxygen here. Now clearly there are other ways of drawing this. You could have that oxygen at that end, for example. You could perhaps draw this without drawing in this displayed formula here. So just to write CO. But fundamentally you're getting 1 mark for that. It also asks what type of polymerization is involved. And this is, of course, the loss of HCl, so that is condensation. Condensation polymerization. Condensation polymerization. Okay, we then move on to how would you distinguish between J and K? J is a dione, diketone, and K has both a ketone group and an aldehyde group. So as soon as you see this as an aldehyde group, you would consider toluenes. You could also use phthalings. You could actually use acidified potassium dichromate, but toluenes is the obvious one to use. And so J would, of course, be no visible change, using that expression that they like, no visible change. And K, because it is an aldehyde, will give a silver mirror. So how many of the 5 marks will that achieve? Probably at this stage we're talking about 3, 1 for the name of the reagent and 2 for the correct observations. But how would you distinguish it using proton NMR? This is actually quite straightforward. There are here, these, because of the symmetry through this point here, we can see that these protons and these protons are the same, or in the same environment, and so therefore we have only 1 peak, and these are different, so there are 2 peaks. So J would have 2 peaks, whereas here, these protons, there is less symmetry, there is no symmetry, will have no relationship to these, or this one here. So there are 1, 2, 3, 4 different environments, so K has 4 peaks in the spectrum, and therefore you can distinguish very easily between them. Finally, a rather complicated question about deciding upon a series of structures. There's 5 structures for you to elucidate. L is just a straightforward, so L is relatively straightforward, you've just got to draw it. So it's a propenoate, which means that it must have 3 carbons. Propenoate means that it would have a double bond. If it's going to be propenoate, this would be an oxygen in that position, which means this cannot be the double bond, of course, which means that would have to be the double bond. So it is 2-methyl propanoate. So if this is carbon number 1, this would be carbon number 2. So that would be the position of a CH3 group. This would have 2 hydrogens on it there. And then it's methyl 2-methyl propenoate, which means that, of course, this is just a methyl group in this position here. So that is the structure of the methyl 2-methyl propenoate. Okay, and obviously you could draw that with a different structure. M is an ester which shows EZ isomerism. So you know straight away that it has got a C double bond O, and there must be carbons on both sides of this. So in order to produce EZ, we also know that we must have a double bond. So we could try putting a double bond perhaps into the same position as the one above. So that if we go to a double bond in this position, to have EZ isomerism, we can't have the same 2 groups on this carbon, or indeed the same 2 groups. So that's not likely because we're only dealing with 2 oxygens up here. So we can't have 2 groups which are the same. So one obvious thing that might be done is to put a CH3 perhaps on that side and an H on that side. And then if we were to put perhaps an H into this position here, we've created something definitely with an EZ isomerism. And so we've used 1, 2, 3, 4 carbon so far. We've got 5 to play around with, so that would be a methyl version of that. So this wouldn't be the only answer for M, but it definitely is one answer. It is one answer. And the reason why it is one answer, of course, is because you have got two different groups on that carbon, two different groups on that carbon around a double bond, so it shows EZ isomerism. The whole of this structure could be the other way around, so it could go, rather than hitting the C then double bond O, it could go O then C double bond O and then CH3. That would work as well. That's another option. And actually you could even drop this one, I guess, to be a no, if you do it the other way around, if this was O, C double bond O, you could actually just put an H there and have that as a CH3. So there's probably about three options. There may be more actually. Yes, there can be more, of course, because you could bring C. This one could become C2H5 as well. So there's probably around about 5 different options for that. But you've just got to make sure that around the double bond, first of all, it must be C5H8O2, but around the double bond, there mustn't have two groups the same on the same carbon of the double bond. N is a carboxylic acid with a branched carbon chain and does not show stereoisomerism. So when you come to this one, you've got to have a carboxylic acid and a double bond. So let's try to have the double bond in the same position as we've had all the way through. So if we have the carboxylic acid in that position, can we create it so that it does not have EZ isomerism, stereoisomerism, or indeed optical isomerism? We can avoid, if we were to put the CH3s here, so you have the same group around the carbon of the double bond, then you have avoided instantly any EZ isomerism. And you've got 1, 2, 3, 4, 5 carbons already used, so we could assume that this is going to be a hydrogen. And so we have the correct formula, and we have the 2 oxygens, and so this would be a perfectly acceptable answer for this one for N. Are there any other variations? I imagine these 2 could be hydrogens, and therefore you would have to either extend this one to CH3, or you could put in an extra CH2 in that position there. There'll probably be about 3 different options for that particular answer. Okay, but that is definitely one which is correct. P is an optically active carboxylic acid. So we have to go back to the situation where we have got here. It looks difficult to create optical isomerism by having the COH directly next door to here, because you haven't got a carbon that could be attached to 4 different groups, because the double bond is not in a good position for that. So I think we would need to try with this one to make this carbon next to that group the optically active one. So to do that, we need 4 different groups around that carbon. So different groups that we could have around that carbon would be that we could work the C double bond C here. So we'd have H, and this would be H2. But we've already used 4 carbons. So at this point, we would have to make one of these CH3, which works rather nicely, and that one would be an H there. So that you have created the optically active molecule, because you've created a chiral carbon, an asymmetric carbon, in this position here. And finally, for Q is a cyclic compound that contains a ketone group and only has 2 peaks in its NMR spectrum. So it's a cyclic ketone. So we could work on the idea that it would have all the carbons, all 5 carbons, in a ring. However, it only has 2 peaks. That means there must be considerable symmetry in this particular example. So if we were to put the ketone group there, we know that there has to be carbons in those 2 positions there, because we know it's a ketone. To create symmetry, if we've got, if we were to put, it's only got 2 peaks for proton NMR. If we make these 2 CH2, we need some symmetry. So one simple way of doing that would be to put these next 2 carbons in that position and put the extra oxygen that we haven't yet accounted for in that position. And then we would have this CH2 and this CH2 would be equivalent because of the symmetry. And this CH2 and this CH2 would also be equivalent because of the symmetry of the molecule. And again, does it add up to C5H8O? Well, of course, you can only have two environments for these protons, and so that, of course, is a correct answer for Q. It probably isn't the only correct answer. We can probably create symmetry in other ways, perhaps by not putting one of these CH2. So you could possibly, with Q, you could possibly do this, perhaps, to create the same sort of symmetry. Do the COC like that, but then on these carbons here we might perhaps put the hydrogen and a CH3 group, so that you have only two different environments of proton. That's the proton there and the protons on the CH3. That would work as well. And there may be other options that you can do around this four-membered cyclic group. So for example, you could in fact have you could have two CH3s in that position. So actually you could go one stage further. You could go C double bond O. You could then attach to this carbon here. You can go through the single bond oxygen there, and then rather than have the two carbons on different sides, you could have them on the same side, in which case all 6 of those protons would be the same, and these 2 protons here would be the same within the structure. So any of those would be right, and that's where you achieve the 5 marks for this particular question. Quite a complicated question.